Morning, astronomy students. Welcome to week 11 of astronomy. This week is an important week. We have a lot of materials to cover through this week. And actually, it has an importance in a sense that it is going to help us understand. So let me first of all, I'm trying to get into the class. It's going to help us basically understand the tools used by astronomers to determine the composition of stars, the temperature of a star, how far the star is, the size of the star, how old the star is, and basically the size of the universe, if you want to, the distance of the galaxy. So we learn a lot. We know a lot about the universe today, not because we can travel. As a matter of fact, we are in this very, very basically tiny object in the entire universe, which is planet Earth, where we cannot even extend our hands to even reach our own star. So we cannot even do anything with our own star, let alone talk about stars and galaxies and black holes and neutron stars and all kinds of things. So it's really always, I mean, it's amazing to be able to be in this portion of the universe when you look at the big size of this universe and be able to say we know so much about the universe. Because how do we know all of these things? Okay, how can we be confident in the fact that what we know is the actual truth about the universe in terms of its size, in terms of its composition, in terms of how far things are, in terms of how big they are, how massive they are, and so on and so forth. The tools we learned before, especially Kepler's laws, they were very helpful to determining, for example, the masses, if we know the relative motions and things like that. But how do we know the motions? How do we know the velocities? So that is really usually, it's an interconnected topic that we have to use. And the answer to that, it's no big secret. We use light. Okay. Light in the visible range where you and I can see, that is the normal light that we talk about. Okay. But light actually comes in a different frequencies that we can't see. There are ranges that fall short of the visible range in terms of wavelength, and namely the ultraviolet. It's a lot shorter than the violet in terms of wavelength. You can see violet, but we can see the ultraviolet. X-rays, which are even shorter wavelength than the ultraviolet. Okay. And gamma rays that are even ridiculously smaller than the aforementioned ranges. Okay. Then on the other side of the spectrum, you have longer wavelength than the longest we can see, which is the red. We have the infrared, which is even longer wavelength than the red. We have the microwave, which is even longer than that of an infrared. And we have the radio waves that are of the order of hundreds of meters, probably kilometers long, okay? And even more than that. So the spectrum itself spans a whole big range, okay? Spans a whole big range of radiation. Our eyes have evolved to be sensitive only between the red and the violet, for a reason probably has to do with the sun, because the sun peaks around those frequencies. That is where it peaks in terms of its emission spectrum. Our eyes evolved somehow to be sensitive to that region. Anything outside of this region, it's less in terms of intensity coming from the sun, so our eye probably did not evolve to capture those frequencies. Okay, so let me share with you, first of all, the objectives for this week so that we're all on the same page. We have 4 units for this week, so it's very important to get on top of them. There will be a homework assignment from this week, so definitely you're supposed to get into them. So let me share Let me switch to the student view because I'd like to see it from your vantage point so that you guys see exactly, so that I see exactly what you guys see. Okay, there was an issue earlier in the day with the internet, so if it stops working, so please do not leave. That means I am working, trying to get it to come back, okay? So anyway, so these are the objectives, the content, the review from the previous week. This will be in a custom 2. Okay, remember the previous week still dealt with the planets, basically the outer moons, the outer satellites, and also the comets. And that closes the book on the solar system. We're moving toward now the stars. We're moving toward the black holes, toward the neutron stars, the galaxy as a whole, other galaxies in our local cluster, and then we're going to even talk about the universe as a whole and talk about cosmology and how the universe evolves. But the key question, how do we know these things? Is it just speculation? Is it somebody just basically thinking that has to be this way? Or there is solid foundation for it? And that's really the purpose of this units from this week. So the units that we're going to be dealing with are units 22, 23, 24, and 25, and they deal with the same topic, basically. They are all dealing with the electromagnetic radiation. So the fact that I mentioned light in the beginning, light is just a special case of the electromagnetic radiation, okay? So let me talk about the objectives first of all. I think there was an issue in here earlier with this link. It did not work. So let me see. It's not working again. So let me fix it. When I was testing it with the previous class, so it did not work. So let me edit this thing in here and let me remove this one. And let me delete it. Okay, and let me insert the link again. Course link, assignments. So you're watching me basically do what I'm supposed to do. Anyway, so this is the project that we're supposed to pick up from here. And let me save this one, save. Okay, if any of these links do not work, please let me know, okay? I think probably they should work, but if there is a problem with them, please let me know. Anyway, this is the objectives for this week. One of the things that you should be careful with, you should note in here is the assignment for the retrograde was supposed to be due last weekend, but I extended it because there was a question actually that came about, and it's a very important question. So let me click on it to go to it. And the question is actually in the instructions, okay? And I edited this activity, but I forgot to mention that this is actually an in-class activity. When we are in class, we'll be provided with Sky Atlas, and then you're going to determine what these stars are. The dots in here that you see in the graph, okay? But this is not a question that was asked from you to do. The questions that are asked for you to report to are the questions that are labeled question 1 and 2 and so on and so forth. So ignore this question in here that is embedded in the text, okay? So you don't really need to identify the stars. And I think I made it clear during the instructions that you don't need to do that. So all you have to do is take the data, which was another question that some of you asked. Are we supposed to plot all the data? Absolutely, yes. So we're going to go through systematically through the entire data. Let's say, for example, July 10th, 2005, you have the right ascension, you have the declination. Use the right ascension in here, and the declination, you're going to find the position of Mars on that date. And you're going to move point by point in here on the graph, on the table, to plotting the different points on different dates. And you will see it. For example, I don't know, January 30th, 2006, that's the right ascension, and this is the declination. So 3 hours and 13 minutes. This is 3 hours, 10 minutes, 13 minutes is in here. And 19 degrees and 54 minutes. So 19 degrees is somewhere in here. This is 19. 45 is almost 45 minutes is almost 20 degrees, by the way. 3/4 of the way. Okay. Sorry about that. Anyway, the point being in here is, that's a reminder of something. The point being in here is that this assignment has been changed for the reason that there was a little bit of couple of questions that I shared with you guys to make sure that you know about them. So I extended the assignment a little bit so that you guys can have more time to go through it. Okay, so that's one thing. The other thing also is that in here you have the typical objectives for this week. So as you can see in here, there are quite a few of them. So I really need to go through them to explain what they are, but this is what you're supposed to know at the end of the day. So let's go into details about this thing. So let me go back home. And am I sharing? I think I am, but I need to go to the student view anyway, because I want to make sure that you guys can see these things, okay? So again, this is the content. Of course, the discussion is going to be posted in here, so hopefully, guys, you will have no questions about it. And the review from the previous units, and these are the PowerPoints summary of these units. Again, and I mentioned that several times before, please read the units, because especially this ones in here, they're extremely important because they help you understand the rest of the course, okay? So let me get into the, oh, I'm sorry, we did the objectives. So let's get into the content. So we have 5 laws to discover in this chapter. I mean, we're talking about the Kepler's laws before and how they help us understand the motion of the planets around the sun and things like that. But we're using light now, and light requires this laws. First law is the dispersion law. This book uses the nu for the frequency, which is typically used in advanced physics books and science books. For the frequency, they use the symbol nu, the Greek letter nu, okay? Sometimes you see me use the letter F for the frequency, and some other people also, some other textbooks, they use F for the frequency. It doesn't matter, it's the same symbol. Times the wavelength, which is typically the lambda, the Greek letter lambda. So lambda times the frequency, whichever symbol you use, is a constant number. It's the speed of light, 3 × 10⁸ meters per second. So from here, this expression helps me find the wavelength if I know the frequency, or help me find the frequency if I know the wavelength. Let's say, for example, the case of a blue light. Blue light is 500 nanometers. We can use this formula to find the frequency that goes with it, because this is a constant. This is just the speed of light, 300,000 kilometers per second or 300 million meters per second. Whichever way you write it, it's the same number. But since we're doing SI, we typically use 300 million meters per second. Anyway, so if we plug into this expression, we should be able to find the frequency. The frequency is a very, very high number. It's 10⁻14 hertz. So it's about 600 terahertz. It's a big, big, big frequency, okay? This is to be contrasted with what we use typically in day-to-day business. For example, the infrared for the remote control, for example, for a TV or your cell phone or your wireless phone, for example, at home, which use frequencies of the order of a gigahertz. Let's take, for example, 2.4 gigahertz. And the question is asked in here, what is the wavelength associated with it? Note this wavelength for the blue light is 500 nanometers. It's half micrometer. Piece of hair, for example, is many times bigger than this one. Actually, this wavelength is smaller than a virus in size. Okay. But this wavelength, if you do the calculation for the one that is used for cell phones, for example, would be of the order of centimeter. So if I use the same formula, the dispersion law, I can find what lambda is. And from here, plug in just the numbers, basically. And the answer is going to be in meters, because the hertz is actually 1/2. 1/2 cancel 1/2, so the answer is going to be in a meter. Convert the meter to centimeters, is going to be 12.5 centimeters. 12.5 centimeters. Where is the ruler? I had a ruler in here somewhere. I don't know what it is right now. I don't see it. Here. here, 12.5 centimeters. So this is centimeters. So it's about this distance from here to here. That's what is used for telecommunications, basically, signal or your cell phone. So it's a long wavelength. Compare that to visible light, for example, a blue light, which is half a micrometer, 500 nanometers. It's a very, very small number. Okay. So if somebody is worried about the 5G signal somehow causing corona or causing all kinds of health issues, they really should be worried more about the blue light, because the blue light has more energy in it and technically should cause more problems than the 5G signal. I don't buy that argument at all. I think it's nonsense, at least from this perspective in here. Okay, so this is one thing that we need to remember. So this is called the dispersion law. It's true always whenever there is a wave and the wave is behaving in a harmonic fashion, basically oscillating. So this is the dispersion law is true always, where the frequency and the wavelength, the product of them is equal to the speed of that wave. And in this case, it's light that we're dealing with. So that's why the speed of light in here is coming. The other law that we need to remember is this law that relates the frequency and the energy. The frequency and energy are basically the same thing. And the only difference between them is this constant. This constant is called Planck's constant, okay? And this constant is just a number. Just like the speed of light is just a number, 3 times 10 to the power 8 meter per second. This happened to be 6.626 times 10 to the negative 34 joule second, okay? Just another number. It's a constant, actually, one of the fundamental constants in nature. Just like this 3 times 10 to the power 8. I mean, somebody might be saying, okay, it's not exactly 300,000 kilometers, it's 299,974 point something. Well, approximately not 300,000. Same thing in here, I'm using approximate number 6.63, okay, times 10. With 2 sig figs, that's good enough. 3 sig figs, that's good enough in this case. Okay, 2 decimal points, that's fine enough for our calculations. But sometimes we'll really need to have a higher precision in here in this one, so probably can get more and more precision in it. But forget about that. For right now, it's just a constant. Just like that big G when we were doing the universal law of gravitation, G happened to be 6.67 times 10 to the negative 11. That too is a constant. It's one of the constants of nature. That's how the universe came up to be. For example, pi is 3.14, just another constant. Okay, so those are fundamental constants. Pi happened to be the ratio of the circumference of a circle over its diameter, which is always the same, no matter how big the circle is or how small it is. You go around the circumference and you divide it by the diameter, it's always pi, no matter what you do to it. Same thing with these things in here. So we take the energy of a single photon, in this case, it's particles of light, and you divide it by its frequency, you will find the number is always 6.63 times 10 to the negative 34. Except in here, it has units. And the first case for the circumference and the diameter, the ratio is just a fixed number. 3.14 doesn't have units because the circumference is in meters and the diameter is in meters. So meter cancel meter, and then the ratio is going to be fixed. If you measure the circumference in inches and the diameter in inches, again, inches over inches, it cancel, and it's going to be fixed number 3.14. Okay. And again, somebody might say, okay, it's not really 3.14, but it's 3.1457 or some other numbers in there, because that's actually an irrational number that never ends. That's just an approximation. We're just taking 2 decimal points after the two values after the decimal point. Okay. So just a constant. Think of them as just a constant. That's how nature cooked itself. Okay. So that these things are always fixed. They don't change. The bottom line in here is frequency and energy are the same. So the higher the frequency, the higher the energy of the wave. That's what this thing matters. That's what it matters. Because this is just a number. Okay? H is just a number. Okay? Which gives me now the entire spectrum. If we take Maxwell's equations and solve them, this is what's going on. If you take a star, for example, star is made up of different particles, among other things. At the outer, basically, surface of it, there are electrons moving back and forth, and those electrons, they produce light. Simplistic picture. As a matter of fact, what's going on inside the core of the star, like the sun, for example, there are nuclear reactions, and we're going to get into them in more detail later on. And those nuclear reactions, they cause basically, they emit, among other things, extremely high energetic wavelengths. And those energetic wavelengths, they go and bounce into the electrons, and that they would change their frequency for the case of the sun until by the time they reach the surface of the sun, they are emitted and they come out of the surface of the sun. So once they come out of the surface of the sun, what causes them to begin with is some nuclear reactions or some processes that were created in there, okay? Now, the radiation that comes to us using the following principle. The electric field, because of the charges moving back and forth, is created moving back and forth. Because the charge is going up and down, the electric field goes up and down. Well, Maxwell's equations basically suggest that if an electric field changes with time, it's going to induce a perpendicular magnetic field that is going to be also time dependent. Also, Maxwell's equations, all of the equations say that if there is a magnetic field that changes with time, it's going to induce actually an electric field that is going to be perpendicular to it and also changing with time. So here is a picture of it. From the source, you have an electric field that creates a magnetic field, that creates an electric field, that creates a magnetic field, that creates an electric field, that creates a magnetic field. So hopefully you get the picture now, and they are both moving away from the source toward you. So it's really this electric field which changes with time, and that creates a magnetic field that changes with time, which creates an electric field that changes with time, which creates a magnetic field that changes with time. And both of them are the electromagnetic wave. That is what light is. So it's an electric field and a magnetic field that fluctuates with time, and each and every one of them is creating the other one. So which one comes first doesn't matter, okay? But both of them now, they're coming to you at the end of the day. So this is the electromagnetic spectrum. In that spectrum, there is the visible light. This is how we evolved as a species on Earth to be sensitive to that range. Why? Because the sun peaks around somewhere in here. That is a maximum radiation that is received by the sun. And then it starts to spread a little, and then as it spreads, it's going to be less and less. Because of that, we're sensitive to that range. So that is the visible spectrum. That is what we see with our own eyes. Okay. Frequencies that are higher, remember, as the frequency becomes higher, the energy is higher. So energies that are higher, and because the frequencies are higher, the wavelengths are less. Remember, the wavelength is c, which is a constant divided by nu. So if nu is high, lambda is low, lambda is less. So the distance between a crest and a crest, or a trough and a trough, is less and less, as you can clearly see from this picture in here. Okay. So that is where this whole thing is coming from. So the wavelength is less in here, and the wavelength is longer on this side. The energy is higher in here because the frequency is higher in here, and the energy is less on this side because the frequency is less on this side. So that's the spectrum. Part of the objectives is to be familiar with some of this ranges. Okay? Of course, the visible light sits in a narrow band in the entire spectrum. The ultraviolet, which has more energy in it, shorter wavelength, can cause problems. Okay, so like using for tanning lamp. CAT scan, for example, uses X-rays. So X-rays are actually more energetic, shorter wavelength in the spectrum, and gamma rays are even shorter wavelengths, extremely high energy compared to everything else. This, they involve they involve the nucleus of the atom. This too, they involve the nucleus of the atom somehow, but less energy than the first ones. this, now they start to get into transition for the inner shell of the electrons, or the atoms. This involves actually transitions in the normal shells, actually the not so deep shells. Okay, this they involve the outer shells of the atoms, or even sometimes the oscillation of the atoms. Okay, that's why actually you can use a microwave to cook with, because a microwave uses microwave radiation of long wavelength enough so that they move the atoms, and as the atoms of the molecules of the I need to stop this. I don't know what that is, but it needs to really stop. And I thought I turned off all of the reminders about that. Anyway, the point being in here is it's used to agitate the water molecules, and as they move back and forth, they create heat, and that heat will raise the temperature, and that's how we use microwaves to cook with. We cannot cook, for example, with ultraviolet, because they will not cause the molecules to move. They will cause actually damage to the to the inner shells of the atom, or even they can cause skin problems. So you don't want that to be cooking, but you want this to be cooking with. Okay, so again, you have the infrared and the microwave, which are even longer wavelength, and the radio wave, which is used for telecommunications and long range telecommunications and some other things. They're actually in this range too. FM stations, AM stations, and TV signal, and cell phone is somewhere in here. Okay, and the example we calculated earlier, we found 12.5 centimeters. Remember, this is of the order of a 10 millimeter. That's about 1 centimeter, and this is about a meter. So this is about a 10 centimeter. This is 10 centimeters. We found 12, okay, in the example that I mentioned before here, 12.5 centimeters. So it's really within that range, okay? Whereas when we looked at the blue light, somewhere in here, this is the blue. The blue has a frequency of some 500 nanometers, which is a wavelength, which is a an energy or a frequency of 10 to the power 15 terahertz, basically 600 terahertz. It's even more than that, than a terahertz, 600 times that is. So it's extremely energetic for the blue light as compared to that of the signal that is used by your cell phone. Okay, remote control uses in this range usually. Okay, thermal image, for example, using this range in here for the goggles, for example, and things like that. Okay, so again, this is typically of how things are. Objects, the same object will look different at different wavelengths. Okay, this is a galaxy that if you look at it with the visible light, this is how it looks like. Now, if you change your sensor to pick up different frequencies, the same galaxy, for example, in infrared would look like this. James Webb will operate in this range, more or less, okay? The new telescope that is going to be launched actually in December now. Initially, it was toward the end of this month. It was planned to be the 31st of October, but now I think they moved it to December 18th when it's going to be launched. Anyway, the point being in here is this is how the same galaxy would look like. Look at it in here. It looks the central is bright, and there are some bright objects, bright stars in this galaxy, or bright cluster of stars in this galaxy. But as you look at it in infrared, it looks different. As you look at it actually in radio waves, there are some ring in here that is high intensity, high, if you wish, emission, and also the central point in your image still high intensity radio waves. If you look at the same galaxy now with the ultraviolet, it looks like the two rings in here in addition to the central one. If you look at it in terms of the X-ray, you lose this structure in here. It looks like more of a uniform spherical object actually, where the central is still more brighter in terms of X-ray, and there are some spots in here that are not even visible in the red light in here, that they are high X-ray emission points in here. So there seems to be in here a high energetic emission source versus in the visible light where we cannot see it. So again, the same object can appear with different shapes depending on their. Let me make a big note on the fact that we cannot still see these images with our own naked eye. This is computer enhanced images in a sense that it's giving me the intensity in colors that we can see, because if it takes this one in infrared, it's still completely going to be black if we're going to look at it with our own eyes. But the computer enhances the image in a sense it gives you different fades of red, in this case, different shades of red, because of the fact of how high the frequency is and how low the frequency is. Besides, it gives you the intensity also brighter in some spots that are in the other places, indicating that these are high sources of those frequencies. So that's basically what this thing is. So the computer actually helps you see it. Otherwise, if it were just to take the raw images, all you can see is still this image. That's all with your own eyes. So these are all computer enhanced images, basically on the computer analyzing the source in terms of different frequencies and giving us with a color-coded image that this is how it looks like to you with your own eyes. This is how it's going to look like. Otherwise, we cannot still see the UV radiation. We cannot see even the X-ray in here, okay? So this is some of the things that we can do with this thing. So again, gamma rays, X-rays, UVs, ultraviolet, that is, visible light, infrared, microwave, and radio waves. Those are the different spectra that we need to be accustomed with, okay? So the first task in here actually is to list these ones in here, actually the way they are. Now, the interesting topic in here that is usually as this is actually a pure science, honestly, the black body radiation, because it's a theoretical object that can emit 100% of all the radiation, or if you send it to it, it's going to absorb it. So it's an ideal system that is used to study the emission of light or the emission of radiation by a certain object. It turns out that that model helps us understand two key things. Let me share with you another screen in here because it's important that I share that. Let me stop sharing this. Let me share this screen in here to explain what's going on. So if I have an object that has a given temperature, it's going to emit radiation, and typical emission spectrum, even if we use the black body radiation, is of this type. So depending on the temperature, and so this is the intensity, how much it is used, and the intensity is distributed with the wavelength. So this is the wavelength, lambda, the wavelength. Okay. Obviously, I don't have a zero wavelength, so extremely short wavelengths. This is in the UV and the X-rays, and okay, and this is the high long wavelength, which is now in the radio waves, okay, so on and so forth. It's peaked somewhere in this image in here. So this is the lambda max. This is for a given temperature. You take an element, for example, this piece of iron, for example, and you heat it up. As you heat it up, as you put more and more heat on it, it's going to change color. It's going to be dark, black, and then it's going to change color to red, dark red, then it's going to shift to yellow, then it's going to become white. White is because now all kinds of radiation starts to emit off of it, okay? Provided it doesn't melt, okay? Provided it's still emitting stuff. Okay, so that is what I mean by black body radiation. So it's not something that is magical or anything like that. But this one actually is not an ideal black body radiation because there are all kinds of, because this is, it has to be either 100% emitting or 100% absorbing, and there is no such a thing of 100% of one way or the other. Okay, so if the temperature now is different, this is how the spectrum would look like. First of all, the wavelength for a higher temperature, so this is temperature T1, okay? This is the second temperature. Lambda max now is going to be different, okay? In such a way that T is inversely proportional to lambda max. And this experimental law suggests that this number, 2.9 times 10 to the power, what is it, 6? Or negative 6? Always. Yes, it's positive 6. 10 to the power 6 the main thing in here is that this is in Kelvin, nanometer, and the wavelength actually is in nanometer. These are the units used in here, okay? So whatever wavelength you're given, like 12.5 centimeters in the first example, convert that to nanometers. So how many nanometers that is? 12.5 centimeters. First of all, I better convert it back to meters. Then I have to multiply and divide it by 10 to the power 9. So if I multiply and divide by 10 to the power 9, this number is going to be 1.25 times 10 to the power 8 nanometers. Okay, because 10 to the negative 9 is, so if I am going to find the temperature for that, this is what I should do, really. Okay. So if there is a signal that emits and its peak toward your cell phone is, so what is the temperature of that object? Then I'm going to find this expression, going back into the expression, 2.9 times 10 to the power 6 divided by 1.25 times 10 to the power 8. Of course, the temperature is going to be very, 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 very small. Not zero. We can never have a zero temperature, though. You can never have a 0 Kelvin, but it's going to be a very tiny number. Actually, I can find what that is. 2.9 times 10 to the power 6 divided by 1.25 times 10 to the power 8. What is the power? Okay. And then to the power 8. It's going to be 0.02 Kelvin. That is, if there is an object that emits where you're, and it's peaked. This is the peak wavelength. So there are other wavelengths less than this one. There are other wavelengths more than this one. So less energy on this side and more energy on the other side. The same thing for the different temperature. So the fact that this starts to emit, for example, in white, when you heat it up so much, means that there are wavelengths that are higher than yellow, for example, blue and green and maybe even violet. So green, blue, and violet. And there are frequencies less than the white. For example, you have a yellow color, you have a, what is it, a orangey color, a red color, and so on and so forth. Okay, so that's basically what that thing is. A white color it's not really a color. It's not frequent. There is no frequency associated with it. It's a combination of different colors. That's all. And the lack of colors is what we call black in this case. So that's basically what the combination of there. So the lack of the visible lights. If you don't have anything, it's black. The combination of all of the colors is actually what we call white. So again, this is something that has to do with the colors. So let me go back into the, so this is an important experiment. This is basically what the studies of the black body radiation has yielded. And this is what is known as Wien's displacement law. Some people, they call it Wien's because in German, the W is pronounced V, okay? Displacement law. Why displacement? Because as the temperature gets higher and higher, the wavelength gets less and less. The maximum, okay? So let me stop sharing. Let me go back to the notes where we were and share notes. The other law that is of importance in here is Stefan-Boltzmann Law. Stefan did it experimentally, Mr. Boltzmann explained it theoretically, and here is the deal with that law, with this law. Any object that has a temperature emits light, period. Emits radiation, period. Doesn't have to be visible, but emits radiation nonetheless. So let me go back into my notes in here to explain. Let me share. All of this stuff is very important because it really helps us understand a few things. The power emitted per unit area is given by sigma, which is just a number, times the temperature to the power 4, regardless of what that temperature is. Remember, T, I just made the big fuss over the fact that you cannot have a T equal to 0. So always any object that has a temperature can emit radiation. So if somebody tells you you're radiant, you're absolutely are. And you can find how much radiation you're emitting actually too. Where sigma is just a number, 5.67 times 10 to the negative 8. The units, this one is in watts per meter squared. So this one better be in watts per meter squared. But you have a temperature here in Kelvin to the power 4. So you better have also Kelvin to the power 4 to cancel that Kelvin to the power 4. So this is just a constant. This is not like the first constants I was making a big deal of. This is not like H, which is 6.626 times 10 to the negative 34 joules second. This is not like the big constant we discovered earlier in the class, which is the universal constant, which is 6.67 times 10 to the negative 9. What is it? Newton divided by kilogram squared times meter squared. Okay, so that was another constant that we discovered way back when we did Newton's laws of universal gravity of, and also there is another constant that we discovered, which is the speed of light, which is 3 times 10 to the power 8 meter per second. You don't need to memorize this, but these are some constants of nature. These constants in here that happen to be constant, it's something that is related to these constants, if you wish. It's related to another constant in here, and that is the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs. Okay, so there are a bunch of constants in nature. These are some of them. These are actually the main ones. There is actually a couple of 2 or 3 more, but at least one more that I know of, alpha, but that's another one. Okay, so forget about the other constants for right now, but these are big constants. These are the constants. This is how the universe basically was cooked for us, and they have deep meaning. They have extremely deep meaning, but we don't know why they are the way they are. Okay, that's really one mystery of the universe that people trying to understand. Anyway, this constant sigma in here is another constant. So if somehow I study a star or an object in the sky, and I find the different waves that it emits, these are the wavelengths, and I find that there is, this one is brighter than any others. This is dim, this is even dimmer. This is dim, this is dimmer than this one. This is even dimmer than the first 2. This is dimmer than the first 3, and so on and so forth. So this is my lambda max. From here, I can use the first law to find its temperature, 2.910 to the power 6 divided by this lambda max, provided this lambda max is in nanometer. Okay, if it's not, I convert it to nanometer, no big deal. Okay, so I know the temperature. If I know the temperature, I can tell you how much luminous this object can be, how much radiation is going to emit per unit area. So I can find what this object is, which is sigma, that constant 5.67 times 10 to the power negative 8 times this temperature to the power 4. So now I know a lot about this object just by doing spectral analysis. If I do spectral analysis, if I find this temperature, then I can tell you how much luminous the object is. Let's say, for example, I can tell you how bright it is. I can go outside and look at it and tell you the brightness of the object. Well, the brightness of the object is related to how far light has traveled all the way from the source. Let's say, for example, this is, and traveled this distance d to reach me, to reach the collector that I have in here for the telescope that I'm using to collect the radiation. Well, that light, which is in here, how many watts per meter squared, has spread through the entire sphere, whose radius is just d. So in this case, that brightness is going to be equal to I over 4 pi r squared, 4 pi d squared, where d is the distance squared. Because the brightness of the star initially was localized in a specific point, and that's spread throughout the entire sphere. So my collector is collecting just a portion of the entire thing, not the whole thing. When I go and look at a star, for example, it appears dim, and it will appear dimmer if it's ever further away from me. I mean, if you take a light source, for example, this one, and you move away from it, it's going to appear less and less bright. As a matter of fact, if you move so far away from it, is going to appear. So in here, it's going to be appear to intense. And as you move away from it, light is going to spread all the way until it doesn't cover it anymore. Same thing. Same thing with the stars in here. So this brightness depends on how far the star is and how much bright the object to begin with is. How much its own basically absolute brightness, if you want to call it that way. How much intensity it has, how much energy it's emitting. Obviously, knowing the distance now, or if I don't know the distance, I can find the distance now using this formula. So that's how we can tell how far these things are. If I somehow can find the lambda max using spectral analysis, and then if I find the lambda max, I find the temperature using Stefan-Boltzmann, I can find the intensity, how much energy is supposed to be emitted every second per square meter. And then from there, if I know if I can measure the brightness of the object, then I can tell how far the object is from us. Very simple stuff. Very powerful stuff, I should say. Okay. Furthermore, there is another thing in here that I forgot to mention, which is extremely important. Let's say, for example, this is blue because it's a shorter wavelength, and this is red. Let me use a different colors. So this is blue, and this is red. Obviously, the temperature of the red, because it has a longer wavelength than the blue is a shorter wavelength, so the temperature of the blue, which is this one, should be higher than the temperature of the red, which is this one. So if I look at the sky and I see two stars, one of them is red, reddish color, because that's where it's maxing at. It looks red because that's where the maximum temperature is. And if I look at this one and it looks blue in the night sky, this is actually has higher temperature, higher than this one, which has a lower surface temperature. So that is basically a typical behavior in here. It has to do with the surface temperature. That's what I meant by lambda max, the maximum wavelength, how it looks like. Because when we do spectral analysis, this is what the star will appear, either bluish or reddish or somewhere in between. Or probably it has so high frequency that it becomes so intense that we cannot even see it. But it's probably emitting in the X-ray. So the temperature is ridiculously high. I don't know how high. I think the highest temperature that I can think of for a star is probably about 200,000 Kelvin. The surface temperature, the core can be in the millions of degrees. Okay. But here is the deal, though. If I look at this star and find brighter in the sky than this one is supposed to be brighter if you put them side by side. But if this one appears to be brighter because it's closer to us, or it's bigger because it's bigger in size too, because the size also plays a role in how much energy is emitted per unit area. Anyway, this is some of the tools we use to determine the size, to determine the distance, to determine the color, to determine all kinds of things. And this is not it, though. There is more to the story than this. One of the things that we can use also to determine the composition of a star. To know what is it made up of. If you had a chance to go to a chemistry lab or even a biology lab or even in astronomy lab, you will see the periodic table. Okay, you have hydrogen, you have helium, you have lithium, and the rest of the elements in the periodic table, including carbon and iron and oxygen and nitrogen and the other elements. Each one of them has its unique signature. Each element has a unique signature. If I take the hydrogen, for example, and study the hydrogen atom, I will see that first of all, we have a nucleus and we have an electron. That electron can exist only in specific energy levels. cannot have any kind of energy it wants. It only can have specific values. And let's say, for example, I have a gas of hydrogen, and that hydrogen is calm, not excited, sitting at the lowest temperature that you can think of. Of course, you cannot put it 0 Kelvin, but it's very close from that. Then all of the electrons should really reside in the lower level, where n is equal to 1. Okay, for each hydrogen atom. As the temperature increases, the hydrogen atoms start to bump into one another. Some of these electrons start to move higher to n equals to 2, potentially n equals to 3 if the temperature increases, potentially n equals to 4, potentially n equals to 5. If there is too much agitation going back and forth and temperature is super high, the electrons will be moving so fast that they can be ejected. As a matter of fact, the n equals to infinity, they're gone. They're no longer attached. So in this case, we have an ionization. We reach the ionization point of the hydrogen. So it's not really an infinite temperature. You need just a finite value where the hydrogen actually loses its electron. And if it does, there is a problem now. So you have a proton in here sitting by itself because it lost its electron. That's what a hydrogen atom, it's a proton and electron. So the electron is gone, the proton is left by itself. Both of them are positively charged. They don't want to be next to one another because a star, you have two protons, actually you have a huge number of them, and each one of them is stripped of its own electron because the temperature is so high. It's actually in the millions of degrees. So in this case, they would want to go away. They are trying to basically escape one another. But remember, a star is a huge mass. So it's exercising a huge, tremendous pressure on each and every one side. So it's forcing them to be next to one another, despite of their electrostatic force that doesn't want them to be next to one another. Okay. So that's basically what's going on inside the star. Some of them will fuse, actually. Then we're going to talk about that when the processes involved in the core of the star. But the point being in here is that the hydrogen itself can be excited and can go from an energy, which is the fundamental state of n equals to 1 to n equals to 2 to n equals to 3 and so on and so forth. It doesn't like to be in an excited state. If given a chance, it wants to go back to the ground state, actually. And if it cannot make it all the ground state because of limitations, let's say, for example, with temperature, it would want to go to n equals to 2. That would be your ground state. If the temperature is too high, for example, it cannot really stay there. So it won't really to stay in n equals to 3 and so on and so forth. Here is what we know about the spectral analysis spectrums. The transition between each and every one of these levels will be associated with an emission. So if it was excited at n equals to 3 and would want to go to n equals to 2, it's going to emit radiation whose frequency is equal to basically the energy gap between n equals to 3 and n equals to 2 divided by h. This formula, really. The energy gap is delta E divided by h. This gives me the frequency that is emitted. It happened to be, for the case of hydrogen, to be this red color. This is something we can see. Between n equals to 4 and n equals to 2, the gap is bigger. The frequency is bigger. And since the frequency is bigger, the wavelength is shorter. So in this case, it's actually this bluish color, which is probably what, the cyan. Okay. And from n equals to 5 down to n equals to 2, then it's actually this darker blue, or probably starts to become violet. Okay. And so on and so forth. These are actually different shades of the same color. Because the transition from n equals to 6, as you can clearly see, and n equals to 5, the gap between n6 and 5, and actually between n7 and n6, and between n8 and n6 and n7, and even with n6 and n8 or n6 and n5, is very small. That's why these colors, they don't, the change in energy from this higher level to here, and from the second one to here, it's almost the same. That's why they look similar shades of the same color. Now, if you happen to see a spectrum if you happen to do a spectral analysis and you see this one in here, so you know the only culprit, the only thing that could have potentially emitted this spectrum must be hydrogen. No other element in the universe can do that other than hydrogen. Oxygen has its own signature. Nitrogen has its own signature. Sodium has its own signature. So each element of the periodic table has a unique signature, and its spectral line will be different from that of the hydrogen from any other element in the periodic table. There is another type of spectrum that we can do, and that is, this is the first one I am describing, where the emit is called an emission spectrum. I can do a different process where I have gas of an unknown nature, and I have light coming from the other side, white light. White light is all the frequencies are coming. On the other side, I have, look at the light that is transmitted on the other side from that unknown gas, and I see everything is back from the other side with the exception of the following. I don't see this frequency, it's missing. I don't see this frequency, it's missing. I don't see this frequency, it's missing. And I don't see the other three frequencies, they're all missing. That means as the white light went through the material, some of it was absorbed, and the electrons that were sitting in here, for some of the atoms, they moved in here, others they moved in here, and so on and so forth. So now I can tell you that that unknown gas is actually hydrogen, has hydrogen and then can emit them. So in the second case, it's actually an absorption spectrum, can help me determine the unknown material. Somebody, for example, passed away, and you take the stuff that is in his or her stomach, and you would want to know what did they eat, for example. So you do a spectral analysis similar to this one. And you find out exactly what that person had digested before passing away. So you can tell exactly what it is. So this is used actually in forensic science too. Okay, so this is something that is very useful for us trying to understand what's going on and given what do we have in there and how things are. So this is very, very powerful stuff. So now imagine with me the following scenario. Not only when I did the spectral analysis, find the lambda max to find the temperature and all of that, but found different frequencies for different elements, and it can tell you exactly what the star is made up of. It turns out most of the stars are made up of hydrogen. 75% of the time is hydrogen, 25% of the time is helium, and traces around probably sometimes it's not exactly 75-24, maybe it's 73-24 or something like that, with 1% or 2% of other elements. The rest of it, we need iron and carbon and oxygen and nitrogen and all of the rest of the elements in the periodic table, the 90-something elements that occur in nature by themselves without having to build them in a lab. They represent that small fraction of the whole thing. So that's basically what we know. That's how we know things, because nobody actually went to a star, even our own sun, to be able to come back to us and tell us exactly, here is a sample of the sun, go ahead and analyze it and tell me what it has in it. That's what we do. That's what astronomers do. By the way, modern astronomy is different than the old days. I mean, when you talk about an astronomer in the old days, it's somebody who's probably spending all of his nights basically looking at the skies with some binoculars or some sort of a telescope, looking and trying to scan the sky. People still do that, though, especially amateur astronomers still do that. But professional people in astronomy now, they spend most of their time actually sitting behind the computers, working on punching numbers and trying to analyze data coming from different sources, because computers do all of this with far more efficient than a person does. They can scan more details, and while you went to go and grab your cup of coffee, something might have gone by in front of you, in front of your screen, and you didn't notice it. Or even if it went in front and the intensity was so low you couldn't even see, let alone the fact that I was mentioning frequencies that we cannot see even if we wanted to. Even if we were paying attention fully well 100% and looking, we will not be able to see these frequencies no matter what we do. So again, these are the stuff that is used by astronomers to learn about the night sky and to learn about the objects in the sky, whether we're talking about stars or even galaxies or black holes or even neutron stars and things like that. Okay. Another component in here that we really need to take into account is the Doppler effect, and this really is going to be one of the last points in here that we're going to raise in this chapter, in this actually week. And this is an important phenomenon. All waves do this. All waves do Doppler effect. So what is Doppler effect? I know you know it. I know that you have experienced it because this is a common thing that happens on a day in, day out thing. Okay. We close this window here because I don't need it. So what the Doppler effect is the following. If you're sitting even if you are blindfolded or you're not paying attention, and an emergency vehicle is coming towards you, you can tell it's coming closer and closer, gaining more and more space as it's moving towards you by listening at the pitch. Even if you don't see it, you can tell that the pitch, the frequency is getting higher and higher. Then you can tell that, hey, this thing is approaching, because you know what the siren is. If it's sitting still and not moving, in traffic, for example, you're sitting still watching it, or even if you're not paying attention, you hear a specific tone. As it's moving towards you, the tone gets to get a higher and higher pitch. If it's receding away from you, moving away from you, you can tell it's doing that without even seeing what it is. Just by listening to the pitch, is the tone going lower and lower frequency, basically deeper and deeper of frequency. That is basically what's going on in this case. So that is a Doppler effect in a nutshell. Okay, provided that the object, the source that is emitting the radiation, is moving towards you, then the frequency is getting higher and higher. If the object is moving away from you, then the frequency is getting lower and lower. So what is the principle behind it? Let me explain it. I have here the same light bulb. This is not 5 light bulbs. This is only one. But it's moving. It's not sitting still. It's moving with a fixed speed. Okay. As it is moving, so let's say in position 1, it emits a radiation. In position 2, it moved to 2 and emitted the second signal. Okay. And it moved to position 3 and it emitted the same signal. Position 4 emitted the same signal. And position 5 right now, it's about to emit the next one. So it did not emit it yet, but it's about to do it. Okay. The first one is spread throughout the circle when it sent it. The first one, so this is what it is now. So this is in its past history. So it sent it, and that one spread throughout this big circle that is centered in position 1, and its radius has to do with how long it took for it to travel this whole distance. That's all. The second position, it's actually this circle. It's still a circle, but its center of it is in position 2 now, because it sent it from that point. Now it's spread throughout this entire circle, and it's smaller than the first one because it was sent later in time. So it still did not evolve yet in time to reach where the first one reached. Okay. The third one is actually centered around when it was in position 3, and it still did not evolve as the first two, because again, the fact that it is, I'm sitting in here, I don't know if you guys hear it or not, there is an emergency vehicle right now because I live not too far from a hospital actually. So the point being in here is that, and I can tell it's coming actually, it's getting closer and closer. So this is a Doppler effect that it's basically a case in point, if you wish. And the fourth circle is centered around position 4, and of course it's smaller in radius because it was sent not too long ago. The fourth circle that you don't see yet is because it still has a 0 radius. It's just about to be sent. Okay. If I'm here, if I'm this side, because the source is moving towards me, it's sending this concentric circles, except that the centers are shifted toward me. So the separation between each and every one of them appears to be shorter and shorter. So the wavelength appears to be shorter and shorter. If the wavelength appears to be shorter and shorter, the frequency appears to be higher and higher. Remember, lambda times nu is always constant. So if lambda is getting smaller, the distance between a wavefront and a wavefront is less and less, then the frequency is going to be higher and higher. That is basically what we hear, okay, for sound. And this is true also for light too. So it's going to be shifted toward higher frequencies. It's not that it's going to be blue, but it's shifted towards the blue. It's getting closer to it. On the other side in here, the separation between each and every one of them, because it sensed the first one and moved away from it and sent the second one. So instead of being separated by this wavelength, now they are extended. So they look extended. So the wavelength looks bigger and bigger, so then the frequency has to be less and less. So this is the pitch, the lower pitch. Of course, depending on the angle where you are. The separation will be the smallest straight in the path of the object, and then it's going to be less and less as you move away around the direction until it becomes the smallest. I'm sorry, did I say the smallest? It becomes more and more until it becomes the most when you are directly away from it. So this tells me on how far I am away from it. So this gives me an idea of how to find this velocity. So if a police officer stops you, it's because he or she using this formula, actually a radar gun that uses this technology. Okay, let me explain what's going on with the spectrum in here. If I take the hydrogen atom, for example, if there is hydrogen in that star or in that galaxy that is moving away from us or moving closer to us, and if I take a spectrum, I will not find the red light sitting at 656. For example, it's 650, closer to the blue than where it was before, where it's supposed to be. I don't know at that point it's hydrogen. I need to analyze more. Because if it's 650, it could be another one. It could be, for example, sodium, or it could be potassium or something else. But then I see this frequency that is supposed to be 486. I see it also shifted back in here. And I see also, so that still doesn't tell me it's hydrogen. And I see this frequency is shifted back and everything. It looks like the entire spectrum of hydrogen shifted toward the blue. It looks to me like this star is coming toward me. So the entire spectrum is shifted. Doesn't mean that red is blue anymore, but it's closer to the blue than what it's supposed to be. If I look at this spectrum, for example, and see this one, it's not 656, but 660, for example, nanometers. And this one is 490 nanometers. And this is 438 nanometers. And everything is the same spectrum, except it's actually moved a little, shifted toward the red. Then I know that this galaxy is actually moving away from me. Just by analyzing this one. So I can find actually how fast it's moving using this formula. If I know the phase shift, in here it's about 4 nanometers. I used about 4 nanometers. And if I take this number and divide it by this wavelength, which is 656 for the red, I can find how far that galaxy is moving away from us. So let's do this problem in here. Let's say, for example, we found a galaxy whose wave shift for the red is 4 nanometers. So we can do the math now. So let me stop sharing. Let me share this one. What's happening here? Why it's not private now? Let's say the red, and the red, according to my notes for the spectrum, is 656 nanometers. So it's supposed to be 656 nanometers. But I'm saying delta lambda is about 400 nanometers. This is an example. This is not. So this is something that we're trying to find how far this galaxy is moving away from us. So we can find delta lambda, which is 4 nanometers, divided by lambda, which is 656 nanometers, and multiplied by the speed of light, which is 3 times 10 to the power 8 meters per second. Again, all I did was take VR equals to delta lambda, the change in lambda, the shift in lambda. This is the shift in lambda, divided by the actual wavelength times the speed of light. Use the same unit so that they cancel out in here. Okay, so the speed is going to be in meters per second. So all I have to do now is to find the relative velocity is going to be 3 times 4, which is 12, divided by 656 times 10 to the power 8 meter per second. It's going to be a big velocity, by the way, for a star that has a shift of 4 nanometers. That's going to be a big number. Oh, I'm sorry, I closed the calculator, so that's 12. I should not have done that. So let me get into a mathematics calculator. But I want to know how fast this star is moving. Obviously, I have to do 12 divided by 656, and it's going to be relatively 12 divided by 656. It's 0.018. So it's going to be 1.8. 1.8 times 10 to the power 6 meters per second. Okay, it's a big number, of course it is. So this is moving super fast. So the galaxies, this is how we discovered that the galaxies are actually receding away from us, or 1.8 times 10 to the power 3 kilometers per second. Obviously, it's 1,800 kilometers per second. It's a big speed, of course it is. Okay, delta lambda is big. That's what the police officer, by the way, uses. Except the police officer doesn't use the red color of the. It doesn't use the visible light. The police officer usually they use radio waves. Okay, I don't even think that they use the signal that is in the cell phone that is used. Okay, let's see how much they. Now they can't use cell phone signal because cell phone signal it's still high frequency enough that it's attenuated, and they don't have a powerful enough gun. Usually it uses less than that. So let's say for the sake of argument they use a meter. Lambda is about a meter. Okay, meter wavelength. And let's say, for example, a typical car speed limit is usually about 65 miles per hour. So I'm going to put it about 100 kilometers per hour. So the speed that we want to detect any variation around 100 kilometers per hour, 100 kilometers per hour, which is 100 times 10 to the power 3 meters per hour, and an hour at 3,600 seconds. So this is basically quick conversion to meters per second. So it's going to be 100 divided by 3.6 meter per second. So that's the speed we want to detect. Okay, I already converted it for you guys. Okay, if you think this is too fast, don't worry about it. I'm just taking an example to see the how fast the police officer is. What's the delta lambda that is needed for the police officer? Can we make a gun really to detect the speed of a car? That's really what we want to do. Okay. So delta lambda, according to that formula, is going to be the relative velocity, which I'm going to assume this is it, times the wavelength, which is I took it to be 1 meter. I'm using actually something in the radio range. That's what radar gun uses. Okay, divided by the speed of light. So let's see what that is. Okay, so it's going to be 100 times 1 divided by 1 meter. That is lambda. Divided by 3.6 and divided by the speed of light, which is 3 times 10 to the power 8. Okay, to see what is needed for this one in here. So the answer is going to be in meters. So delta lambda, this is in meter per second, and this is in meter per second. So delta lambda, let me see quickly in here. I'm kind of curious, honestly. I don't know. I have no idea what the radar gun works, what kind of technology it uses, honestly, what kind of signal it uses. So 100 divided by, open parentheses, 3.6 times 3 times 10 to the power 8. It's going to give me some decimal number for sure. It's going to be 9 times 10 to the power negative 8. That's too small of a number. I was thinking, did I make a mistake somewhere in here? It's giving me 9 times 10 to the negative 8 meters. Kilometers per hour. Yeah, that's correct. This is a curiosity of mine. I'm trying to figure out something in what is. So they must be using much longer wavelength than 10 meter, than 1 meter. Probably they must be using much longer the wavelength than what I was thinking. Okay. They must be using a higher wavelength than what I'm thinking. Because this delta lambda is a very small number. This delta lambda is very small number. Delta lambda of the order of 10 to the negative 8 meters, which is 0.9 nanometer, which is probably detectable. I don't know. Maybe 10 meter will be even better wavelength. Maybe 100 meter wavelength will be even better. So you can detect those variations in the wavelength. Again, this is curiosity, okay? Forget about that. In astronomy, we don't use this. We use this number. We use wavelengths of the order of a nanometer, okay? And usually the shifts are significant enough for me to be able to see them. And once we do that, we're gonna find how big this, because these things, they move super fast. And that's how Mr. Hubble detected that the universe is expanding by looking at the expansion of the universe, basically using this technology. Okay, because if I can find the shifts, then if I know the shifts, then I'm in good shape. Then I can find. By the way, he did not use it, and he cannot tell, and you cannot really use this technology for nearby galaxies, because nearby galaxies, it seems whatever governs them is not really governed by the. They don't necessarily move away from us. So the local cluster is not going to work for it, but for faraway galaxies, and we'll get into more detail into these things. But I want you guys to come back to this chapter, to this entire week later on down the road, because a lot of the things we learn in here are going to be useful for us down the road. Of course, you're going to have a homework assignment doing some calculations with these things. And the last point in here to mention is the fact, how can we use this technology to detect the motion of a star? The star, for example, can be spinning around this axis. And if it's spinning fast enough, it will have a high enough delta lambda that we can use to find how fast it's spinning around this axis. If it's spinning like the sun, which is extremely slow, then you're not going to see much shift in the frequency. So again, you're not going to have a high enough sensitive equipment to find that shift. Okay. Same problem that I was running into with the radar technology. I used apparently a short wavelength of 1 meter. That's still not good enough. So I'll probably have to use even different numbers in there. Okay, a longer wavelength. Okay, meaning shorter frequencies. So again, what we're saying in here is the star is spinning. As the star is coming towards you, the wavelengths in this case is going to be shifted towards the blue. As the portion of the star is moving away because it's spinning away from you, the signal will be actually shifted toward the red. So the spectrum looks broadened for a specific frequency. This is the low frequency. This is the receding away. This is this contribution, and this is this contribution. So the actual signal, if the star were not moving at all, were not spinning at all, should be this one. But on one side, there is a plus delta lambda, on the other side, minus delta lambda, causing the whole spectrum to broaden by 2 delta lambda. Using that, the entire broadening, if you wish, of the spectrum, dividing it by 2 and using this formula, I can find the radial velocity in here with which this thing is spinning. And if I know the size, I can find the angular velocity with which it's spinning. So this is the stuff that we can use for. It's not just for how far the objects are and how far the objects are moving away from us, but actually how fast a single star can spin, as long as it's spinning fast enough. If not, then we need other techniques to determine this information. This is in a nutshell the week in here for this week. Please do not forget that you have quite a few other assignments. Also, one of them is your observation for the lunar observation for this week, which is the 3rd observation. So you still have one more after this one, and you're done and you're ready to do your report. Don't forget the retrograde motion. If you didn't do it yet, please finish it and submit it by this week. You also have quiz from the week before, so don't forget to do that. And we will have homework assignments in here. So what are we supposed to do this week? We're supposed to come up with the 5 laws that we have discovered today and summarize them and put them in your own words. So let me write them for you in here. Okay, so let me share. So the first thing that we discovered was the dispersion law. That says the wavelength times the frequency is just a constant, c. C is just the speed of light, okay? This is one of them. So if I know the wavelength, I can find the frequency and vice versa, because this number is fixed. The second law that we learned also is that the frequency and the energy are related to one another via this constant, where h is just a number. In the book, we can use 6.3 times 10 to the negative 34 joules second. And this one is just a fixed number, which is 3 times 10 to the power 8 meter per second. Okay. So this is the two laws that we have discovered. So the frequency and the energy are the same, basically. Well, this is what that is. The third law that we discovered has to do with the displacement law. So the third law is the displacement law. And this one gives me the temperature of a given object if I know its maximum wavelength. And in here I have 2.9 times 10 to the power 6. And this is in Kelvin nanometer, provided this wavelength is actually measured in nanometers also. So this is the third law that we discovered today. The other law is Stefan Boltzmann. This gives me the energy radiated per unit time per unit area, okay, power per unit area. This one is given by sigma times 10 to the power 4, where sigma is just another constant, which is what, 5.67 times 10 to the negative 8. What is the units again? Watts per meter squared per Kelvin to the power 4. Okay. Temperature is always in Kelvin, and this is something that even my engineering students, I was mentioning before, sometimes they forget to work with. So this is one of that makes it a little bit hard to work with. So this expression is a little bit not so obvious. The fifth one that we discovered today is actually if I know the shift in the wavelength delta lambda, I can divide it by lambda and multiply it by the speed of light. And from here, we can find that relative velocity of an object compared to the observer. So I have a source in here. I have an observer. And is this observer going to, the source is going to the observer, or the observer going to the source? Could be the same thing, by the way, too. Or is it moving away from him? That is determined by the sign of delta lambda. Is delta lambda going toward the blue or delta lambda going to the red? If it is going to the red, it's moving away from you. If it's going to the blue, it's moving towards you. Okay. And the actual velocity with which it's moving is given by this expression. So this is the shift in frequency, the shift in wavelength. And this is the actual wavelength. And this is the speed of light, the same constant we've been dealing with. And this is the relative velocity. Again, this is in a nutshell the laws that were discovered. This could be very, very, very ugly very quickly if we really are not careful in here, because it involves a lot of math and sometimes that can be confusing. So we're going to approach it a little bit carefully in this week. So we just are going to have some specific assignments for the homework, and we're going to have a special session for the homework assignment from this week, because I believe, and this is not my belief, this is actually true for all science, numbers tell you the story in detail. I mean, we can talk and talk and talk and talk, but if we don't have numbers and if we don't see something, we're never going to be able to have a sense of what it is. That's why it's important to have practice numbers, because the numbers tell you the whole story and nothing more and nothing less. Okay. That's why it's important that we have to have a homework assignment from this week. And hopefully that homework assignment will be enough to get us into this 5 laws. So again, the task is to put them in your own words. I mentioned them to you. these 5 laws that we discussed them today, starting with the dispersion law. The law in here that is relating, this is actually due to Mr. Einstein, who was trying to study the photoelectric effect. Okay, but it was known from before from Mr. Planck, who tried to explain something that has to do with the phenomenon that I mentioned before, the blackbody radiation. The blackbody radiation was actually historically was a big problem. They tried to explain it with classical physics, and there was a disaster in this low frequency things. It was known as the ultraviolet catastrophe. Ultraviolet catastrophe, the experiment was showing this pattern, but the theory was blowing up for low frequencies. I mean, lambda, yeah, getting for low frequencies, for high frequencies, for short wavelength, was blowing up. That's why it was called the ultraviolet catastrophe. At that time, in the late 1900s, in late 1800s, we didn't know about the X-rays to be able to talk about X-rays. So they were actually measuring things with the ultraviolet, and that's where this problem there. So Mr. Planck introduced a constant H, and it explained then this pattern beautifully. And then Mr. Einstein later on used the same trick that Mr. Planck used actually to explain the photoelectric effect. So he used this law for the photoelectric effect. Okay. Later on, it became actually one of the fundamental laws for light, for the electromagnetism in general. Okay. And then this is actually due to Mr. Wien. Again, you can take this curve in here that Mr. actually Planck has developed later on to explain things, and you can take something in calculus, they call it derivative, and you can find that lambda max, and it works beautifully. Actually, it matches sensationally. Okay, but Mr. Wien discovered it experimentally, so that's what it is. And then Boltzmann Stefan law in here, all you have to do is basically sum the entire area in here, covered in here for this distribution. This is what Boltzmann law is. And actually in the book, they give you a picture of what that looks like by shading this area. And that is what Stefan Boltzmann law is. So it gives you the entire radiation emitted per unit area. Okay. And finally, this one actually, usually the expression is a little bit more complicated for high velocities, but most of the time is, even for the case of the galaxy that I took earlier moving super fast, the velocity was not high enough. I mean, it's big. It was in the millions of kilometers, millions of meters per second, or thousands of kilometers per second. Where's the example I took? It was 1,800 kilometers per second for a galaxy. And even that is small relatively compared to the speed of light, okay? So when I used it shifted by 4 nanometers, the speed was 1,800 kilometers per second. Even that number is small to the speed of light. So this is beautiful, this works, okay? The Doppler effect is really a little bit more complicated in terms of mathematics, but this is what we're gonna be using for our purposes, okay? I know this is a little bit longer than usual in terms of recordings, but because the units are, first of all, 4 units, which you're required to do the reading for. And also we have more examples coming down the road with a little bit of applications from the homework assignment that you're going to be seeing. The homework assignment, again, as usual, you're going to see it next week with a review from this week, and you're going to have the assignment for you guys. Okay, let me stop the recording. Glad it did go without any kind of disruption. And watch for the announcement, please, for the extra session on the homework. Thank you.